My name is Dr. Joyce Blueford. I'm a geologist and I'm kind of retired. I used to work in Russia in oil country. I used to also work for the U.S. Geological Survey, doing mainly research with micro fossils. So actually a paleontologist. But today we're going to look at the Hayward Fault in Fremont. I want to make sure that you guys understand as you walk around, many times you're crossing the Hayward Fault many, many times. How do we know that? Well, if you look at this map here, you'll notice these little circles, the orange circles. Those represent earthquakes that occurred over like 10 years. And this helps us to define where the fault actually is, realizing that the earth is not perfect, so it doesn't always occur in the same place. If you look at this map, you'll see that there are areas where there is no um, earthquakes at all. And then there's other places where there's many. And so this gives us a clue of what's going on in the Bay Area. Now, this is a basic map of the San Francisco Bay Area. We have the bay in the middle here. And the Hayward Fault, the star is where we live. But this is part of the San Andreas Fault system. This whole group of faults, from the Greenville Fault over to the San Gregorio Fault, is the plate boundary. It's a transform fault, which I'll go over in a little bit, but that whole area is the fault boundary. We are part of that fault boundary and we are slipping by each other. Now, I want to go over how earthquakes actually form and why our Earth is full of these earthquakes. Basically, it's because we have stresses on our Earth. We have the rotation of the Earth like this that's occurring at the equator. It goes much, much faster. It goes about 1,000 miles per hour versus at the poles, it's almost going to 0 miles an hour. And that causes stress on this very, very thin layer that we call the lithosphere. And that lithosphere, and I'll show you a picture about it in a minute, is the depth of the plate boundaries. Okay, we also have internal stresses, mainly caused by gravity. You've got to remember our Earth, as it's spinning around, you have forces pushing us down. Otherwise, we wouldn't even be on this Earth. We would be out in space if our Earth stopped spinning. So we're going to look at these forces together. So I want to make sure we have our vocabulary straight, that there's the division of spheres. You have the atmosphere, which is air we breathe. It's an envelope around our Earth. Not all planets have this wonderful envelope. We have the hydrosphere, which is water from salt water to fresh water. We have what we call, and if you look at this area here, and this is exaggerated, guys, so this is really, you'd hardly see it in a cartoon map like this. We have the asthenosphere. That is a layer of the earth, which is the upper mantle and crust. That is it uses the word ductile. That means it's moving. And that is what the plates basically ride on. And then, of course, we have the lithosphere. The lithosphere is more rigid and it is floating, and I put that in quotes. It's not like if you're floating on water. It's a different kind of float, but it's less it's more dense than the asthenosphere on which it is floating. Now, we also want to make sure this is a different system of the spheres versus the core, inner core, which is this one here, the red. Then you have the brown, which is the outer core. And then you have the mantle. And then you have the crust, which is a very small part, this kind of light brown. So this is how we break it up. At one time, we just used the division of the earth, but then we realized that the plates act differently. It's almost, if you look at this picture here in the lower mantle, it's acting a little bit differently than we are thinking. Researchers are working all the time on trying to figure this interrelationship. Realize we do not know everything about our inner Earth at all. Okay, so let's look at these stresses again. External stress. Our Earth is rotating and revolving, and that causes differentials in how pressure affects us. You know, gravity is pulling things away. I mean, that's, for instance, the tides. Those are caused by gravity, gravitational attraction of the moon. So that's here. And then we've got to remember we're rotating on an axis. Things are moving faster, slower, and it responds. The asthenosphere and the lithosphere react to this changes. Mind you, deep in the earth, that's a different story. In this cartoon here, and again, it's exaggerated, the asthenosphere is just a little blip underneath here. This probably shows it a little bit more. But you have this convection currents. Convection currents is caused by heat. Anytime you have a ball spinning around, gravity, which we don't know a lot about. Gravity is probably in the future, you guys will probably be inventing new things from gravity as we understand that force. We don't understand it fully, but it creates heat, and that heat creates things like volcanoes. It causes our plates to move around. Okay, now let's look at this very famous map. It's called the Dynamic Earth by scientists from the USGS. It's the plots of all the earthquakes and volcanoes that occurred over 50 years. This is from, I think, 1960s to 2000. And if you look over here, the black represents the earthquakes. The red represents volcanoes. And if you notice, there's a lot more earthquakes occurring than volcanoes. Volcanoes are in specific areas, like here we have it, we call it a hotspot in the Hawaiian Islands. We have volcanoes in Central America, in Northern California, starting with Shasta and Mount St. Helens, we have volcanoes. So they're all kind of in between, but earthquakes, the cracking of the earth, and just realize that that's what an earthquake is. It's when the earth moves. And so when a volcano is doing its thing, it also creates movement. So notice though, things that are missing. Look at Africa here. You only have it in this area in the east coast of Africa, but in the central part, there's nothing. And we also know that it seems like Africa is not moving anywhere as we look at these plates. And so these define the plates. It's not scientists making a direct line. It moves all the time. Some scientists divide the earth in many, many plates, but some do not. Okay, so we have two things that are created by this dynamic earth. We have geophysical evidence. That means, like if you look at this picture of the 1906 earthquake, the people are walking around, but nothing actually physically is happening. Geophysics means the waves are generated by an earthquake or a volcano, go through an area and leave. Just like on a tsunami, this is a tsunami coming. This would be an earthquake that was way out and creating energy. Once that energy is released, you do not see it anymore. So that's what we call geophysical evidence, and that's mainly our earthquakes. Then we have, what is this? So this is from Hawaii. This is structural evidence. So as a geologist, we can go back in time and look for these kind of rocks, and we can tell if volcanoes have turned on or turned off. Matter of fact, that is exactly what it does, and it helps us plot how the plates are moving. So this is what we call structural evidence. It's stuff that's still left after the event. Now, let's take a flyover of the Earth. This is a relief map. I want us to look at the Earth the lithosphere without the hydrosphere. And as we notice here, you'll see this is just to give you reference. This is South Africa, I mean South America, and this is the tip of Africa, like Cape Horn here. These are mountains underneath the water. We don't see them, but a lot of people think that the oceans is just a bowl, but it's not. It's super interesting. And this is as we under realize what was going on. That's how we evolved the theory of plate tectonics, which is now fact. So this is going up the Mid-Atlantic Ridge. A lot of earthquakes as the earth is separating along this crack. Now we're going over to Saudi Arabia, India. Now notice India, what is those big mountain ranges? That is the Himalayas. That's when India plate kind of ram into the Eurasian plate. Now notice that there is the Ural Mountains, those small mountains, and then you see very deep structures around um, Italy, Spain. This is where we have earthquakes and volcanoes. And then we come to the United States. Now notice offshore there, we have some very deep trenches. Notice we have uh, the East Coast versus the West Coast. The East Coast is what we call um, it's a land that's going down. It is kind of going down because its tectonics is stopped. But if you look on the West Coast is much more it's uplifting. And yes, this is a cat. Sorry, guys. This is Autumn. She's our local cat. I can't control her. Okay, so our Earth is spherical and we are not getting bigger or smaller. And that's important to understand. And so what happens? This lithosphere is moving, but it can't get bigger or it can't get smaller. And so there's different ways in which these plates interact. We have divergent, meaning that they go apart. That would be your Mid-Atlantic Ridge area. Then we have convergence, they're coming together. The plates can do two things. You can do abduction. An example would be the Himalaya Mountains. That's why they're so high. Or you can have subduction, where an oceanic plate, which is denser, goes underneath a continental plate. And then this creates volcanoes. All of them create earthquakes, however. And then we have this transform. What happens is because we can't get larger or smaller, there's this pressure this way. And so our Earth does these funny things and it changes through times. This is what helps climate change throughout so naturally our Earth would change because of these plates. So the weather change, the climate changes, a lot rests on plate tectonics and understanding this movement. And if you notice, this globe here is going from 65 million years ago. We have this to recent. So this just shows you the movement. And this we have to do, this is one of the tasks of geologists is to try to figure this all out. Okay, divergent. So here we go. Notice, do you understand these mountains and valleys over here in the Mid-Atlantic Ridge? But it cracks because we're spherical and because there's different pressures at different layers. So this is diverging boundary. This is converging boundaries, two type, subduction. And we used to have this along our coast. Right now, California has a subduction zone from Eureka on up toward Washington State. So at one time, the Bay Area had subduction that changed into transform, as we'll understand, as we'll look at. Then we also have the subduction is this one, is this area here. And this as we go down here, coming down and then melting as we're going down, and then we have volcanoes coming up. You have to remember the crust is rigid, but volcanism causes rock that is less dense and it will rise, just like you're seeing here in that first picture. Okay, then we have transform boundary. So here in Fremont, we changed from subduction to transform boundary about starting about 15 million years ago, which then changed how we reacted to things, which is a very complicated story. But if you look at this picture down here, you can see this is the San Andreas Fault System, Pacific Plate, and as this was going up, then we still have subduction. This has a lot of large earthquakes, especially off ground. This is what we call a triple junction. That's where three plate boundaries actually coincide. Okay, so hopefully now we can get to Fremont and let's see what's happening here in Fremont. Again, San Andreas Fault System. One side, the west side, is going north. So they predict maybe in 60 million years or 30 million years, we will be in Eureka. Some of the rocks that we have on this side, the west side of the San Andreas Fault, came all the way from Los Angeles. And so notice in between, the stresses don't just break, it breaks in um, what we call mountains and valleys. And that's an important part. If you ever look, if you get up in the morning, you see Mission Peak, it's a mountain. And then if you look over to the west, you see the valley created by the San Francisco Bay, and that's low. And so we have these things of mountains and valleys. That gives us a first clue that something's going on tectonically. Now let's take a look at this picture. If you go on an aerial, this is just south of us from the Hollister area. And as you can see, you can almost see the crack, but it is not perfect. You got to remember, this crack started maybe 10 to 20 million years ago. And you have things like rain, you have floods, you have gravity changing the surface. And so you have to, as a geologist, you have to go through that and try to figure out what's going on. As we know it now, and it could change, mind you, this is the San Andreas Fault, this big one right here on the map below, that's moving north. But notice how it's going in the earth, that our area is moving south, but with it in the south, the whole area, you have little cracks going north and south. You have to kind of think about this sometimes, how the earth actually moves. This is very difficult to understand sometimes. Now, let's take a look at the evidence that we have here in Fremont. Fremont's kind of unique because Fremont, the whole city, is being ripped apart by the Hayward Fault. Now, the Hayward Fault was not moving about uh, 2 million years ago. All of a sudden, it started to start to rip because the Calaveras Fault, which is near the Sunol Pleasanton area, was moving. And then because things changed, the Hayward Fault in our area started to move rapidly. Actually, it has a lot to do with the extinction of the mammoths and mastodons and saber-toothed cats that used to live in this very lush area with water. But as the earthquakes continue, and we went from subduction to transform, our whole climate changed. Okay, so I'm going to point out, this is the Fremont Earthquake Exhibit. This is Lake Elizabeth. We're going to be taking a virtual tour through there, and I want to show you evidence of what's happened here. And I'm right here in Tule Ponds, which is a small little lake over in this area here, but it's all caused by the Hayward Fault moving. Now notice when you look at it close, it's not a straight line, and I want you to recognize it is not a straight line. And we have homes that have been built on the Hayward Fault. We have lakes that have been offset by the Hayward Fault, and we have roadways that have been offset by the Hayward Fault. And so I want to talk about a very important earthquake, and that was in 1868 on October 21st. At about 8 o'clock in the morning, there was a very hard shake. It rumbled and rumbled for about 30 seconds, which is really long for an earthquake. And it actually ripped from Milpitas all the way to San Leandro, 6 feet. The transform boundary just broke it like this. In some areas in Fremont, like Tule Ponds, there was an uplift. And that caused some, well, as we see, it shows some evidence of this 1868. 1868 is just a little bit after the Civil War. Not many homes were here, but of course the mission was here. And look at what happened. We got to remember they photographs weren't that great back then, but the whole roof, that those little X's up there, one is a cross, but the other X's is the whole roof being shifted. They had to tear it down and build a new one. And you got to remember, UC Berkeley wasn't even around back then. And so there was not that many scientists that actually looked at it. It wasn't until the 1890s that a seismologist, Andrew Lawson from UC Berkeley, came down and documented it. And wasn't until the 1920s, that we actually had pictures. These are actual pictures from the 1868 earthquakes. These were old time pictures, but these were in San Leandro, and San Leandro was devastated, and they had to flatten everything out and rebuild it. Oakland, and it moved to Oakland because there was no big break in Oakland. But here in Fremont, there was a huge break that made Tyson's Lagoon much smaller. And let's take a look. Now, this picture here on the left is in 2019. Because we couldn't have taken a drone picture of Tule Ponds. But you see how this is a 30-second lapse. And see how the breaks occur? If you look at the breaks before, you might not have predicted where that break is. So you have to be real careful on building near areas. This was in Ridgecrest, and there wasn't many people living in this area. But look at the roadway. Roadway was totally broken down. So I'm here. We're going to talk a little bit about Tule Ponds right now. Some of you have been here before. Tyson's Lagoon, which is the larger lake, has been here for at least 4,000 years. This provides us information about what has happened here. Tule Ponds, these three ponds here, this is C, B, and A. These were created to prevent flooding. So that they've only been here for about 20 years. But we're going to concentrate on the data here. Lots of information. This line here, the red line, is the Hayward Fault. It is the creeping part of the Hayward Fault. What did she say? Creeping? Yeah, creeping means that it is slowly moving about 5 millimeters per year. And then we have another trace of the Hayward Fault. It defines what it looks like. Now, just remember where these are because I'm going to show you some video of what they look like today. But this second line is where where the Hayward Fault goes deep inside the earth and goes underneath. It's still moving down there, but it's the hidden trace. It's kind of moved over again because of this movement. Now, why in the world do we have Tyson's Lagoon? And why did I say it's over here for at least 4,000 years? Well, that's because this area used to be almost like a savanna type area with lots of water from the Central Valley. And all this water kind of got stuck here in what we call the Niles Cone. And the blue area is rock, it's sandstone, that actually can hold water um, within its pores, say. And so if you notice here, it says Hayward Fault, and it breaches, it's what we call breach, it breaks the Hayward Fault. And so notice that the water goes up. And that's basically why we've had this fault here for a long time. So what this water is, some of this water can be old as 10 million years old. And this is the lush area, the Niles Cone. You get about a third of your drinking water from this water. And that water can be as old as 1.3 million years ago when it got stored in these rocks. That's when the mastodons and mammals and camels roamed this area. Okay, let's take a look. This is a picture of where the Hayward Fault enters Tyson's Lagoon. You can see we're at the broadest part of Tyson's. So on the other side there, that's what we call the inactive trace of the Hayward Fault. And then what we're standing on right now is where the Hayward Fault comes into the area from
other parts of Fremont.
Okay, so let's take a look here.
We're over at the seasonal wetland, and if you notice that we have stairs here, because it's too steep. When we first got this place in the late 1990s, we weren't sure what it was. But as we started to research, we realized that this is what you call a fault scarp. We're going up the hill now. We're going up about 4 to 5 feet elevation. This was caused by the Hayward Fault in 1868 on October 21st. And this whole area, if you notice, is uplifted. It looks down on Tyson Lagoon, and this was caused by the movement of the Hayward Fault.
Okay, so this is what it looked like in 1920s. This was the fault scarp. So we have this because when we first figured it out, we didn't know what it was, and now we do after unearthing these pictures. Now we also, because of all this findings, we did this trenching, and we were able to look deep inside the earth and look at the sides. Now, if you look behind me, this part here is part of this mud art, and it gives us clues of what happened.
So
So
we're
let's
walking along
continue.
the active trace of the Hayward Fault, and you can see there's been some uplift in this area. This was probably caused by the displacement in 1868. And as we go down our trail, the Hayward Fault would be on our left. Now this too has been artificially built up so we could make a road on there. So urban interference has probably changed the natural contours.
Okay, so this is going back to the trenching. This is what we call seismic stratigraphy. All of those black lines there kind of tell a
This is a
story.
diagram showing all these micro faults, and it helps us decide what is going on. Has there been change through time? Has there been no change through time? And this is how geologists and seismologists figure out how the Earth changes.
Now, if you look there, it says ash swirls and blibs. This is one of the major findings that this trenching did. We were able to identify 7.0 earthquake. So let's take a look at those blibs.
Let's look at a slice of time. This goes back about 400 years, and it shows an Earth that is in flux. What does that mean? It means that it's changing. Those red pieces of yarn show breaks. If you look at the dark gray area and you bring it down, those at one time matched up. This is what we call a fault. They can be large, they can be small. Now as you go up closer and we go over to the right here, we notice some swirls. Now those swirls actually are an area that was ripped up during a major earthquake. And as it settled down quickly, it left those rip-up clasts. Let's take a little look at some other features in this. Now you see the little white things here. Let's take a little closer look at them. If you notice, those are actually shells. And that tells of a time when Tule Ponds was larger. Now how could that be? Well, earthquakes can cause problems. It could shut off water, it could turn on water, it can make things deeper, it can make things shallower. And so this is a record of Tule Ponds.
And it is this record in which we make conclusions. And this was a 10-year study. Okay, now let's go over to Central Park. Hopefully some of you have seen, we have signs there, and we have an earthquake exhibit, which is right now it's closed because of the city closed it. But we have some signs there and spots that show what the Hayward Fault does in an urban setting with cement and asphalt. This is an area.
This is the Stivers Lagoon area. The road I'm zooming in on is Rocket. This is where the Hayward Fault trace you can find. Now as I swing around to the left, the fault actually warping that building there. And as I turn around, we're going into where Stivers Lagoon is right now. The Stivers Lagoon is a depression. It used to be much larger, and is part of what we call a sag pond.
So hopefully you noticed those hills that those homes were on Rocket. This is what it looked like in 1920s. What they did, they didn't realize that this wasn't just a view. They thought that if they built homes there, you would have a nice view of the park, which is the lake, which is artificial. But most of those homes are very close to the Hayward Fault. And I don't think such a great idea. Okay, this
I'm
is
on
looking.
Rocket Drive, going down toward Central Park. Now if you notice, this curve is offset. Hayward Fault goes right through here. If you notice, there's cracks, and as you go across, you start seeing more cracks underneath the red car, over to underneath where the building is. This is evidence that the Hayward Fault is under this area.
Okay, this is, if you've never been to the Fremont earthquake exhibit, it's in the old community center. And when you walk in there, you'll see this very big crack. If you look on the bottom there, it has kind of stripes, like what in the world is that? Is that actually the fault? Yes, it is. In 1962, when this building was made, we didn't really know we knew there was a fault here, but we didn't know what it meant. And so in 1972, after 10 years of stress, it broke. And then this is what you see. So that picture on the left is the first break. A janitor walked in there and goes, "What in the world?" And so what we've done is we've put a big map so people can realize this is what happens when you build on the Hayward Fault. Not a good idea. Now let's take
We
a
are
look.
inside the earthquake exhibit in the community center in Fremont. As you can see, there's a crack in the ground. And what does that crack mean? Well, let's take a little closer to it. Those lines used to be the traces of the tiles. And as you can see, one side seems to be going one way and the other side is going the other way. This is the Hayward Fault.
So again, this is evidence. This is about almost 3 inches offset. So if it happened in 72, then you start calculating, how fast is it going?
Leave the Hayward Fault exhibit. You go to a lake called Lake Elizabeth, and you see mountains in the background. Now, as you turn around, you start seeing just what you think is a patio. But when you start walking closer, you start seeing evidence of breakage. So let's take a look at this wall here. Concentrate down here. You can see something is breaking it. And as you walk along, you notice that the concrete is cracked and it's following the direction of inside. Notice that the wood is bent. That's because different materials have different movement.
So if you look all around Lake Elizabeth, you see evidence. A geologist's eyes is toned in to look for differences. Now, a lot of people will think, well, they built this, but no, this is natural. It's kind of like if you have a pimple and you try to break it, as you put pressure in the area, it starts coming up. And this is what we call a knoll. Now, if we
We are
look,
now on the other side of the knoll. Let's see if there's any evidence of an earthquake. So as we go around, curve is okay. But then in the distance, what do you see? As we get closer and closer, can you see the bend in the curve? Now if we look at the bend and we look around, we start to see a lot of cracks. And these cracks are telling you it's part of the Hayward Fault creeping at about 5 millimeters per year.
so if you take a look at this area here, all throughout Lake Elizabeth, there is cracks and movement, and we've put signs where it tries to direct your eyes. So you can look at this easily because of where the signs are. Okay, then this is an area where the old city hall, I know none of you were around when the city hall was here, but let's take a
Let's
look at
look for
this
more
area.
evidence of the Hayward Fault. As we come along this curve here, you see an offset. And then you see these cracks in the asphalt. And that's showing en echelon faults caused by that slow creeping every year. So as we're going into another area, this is where we dug a huge trench, went down and could see either side of the Hayward Fault. But then as you're going further up, you start seeing a knoll. And that knoll is a compression knoll. And this is where they built the second city hall that in the 1989 earthquake, it was so conflicted and cracked that they had to tear it down.
So this area here, we're going to look at, see this picture on your right. This was in 2006. U.S. Geological Survey was doing a scientific study, and they dug a big trench. And we thought we would open it up to people. And we only could open it up for a few weekends. It was in October, and we had 23,000 people just in a few weekends come all around the country just to see the Hayward Fault. Now, what those lines are and what those papers are basically that stratigraphy that you saw in the map, the one actually that's behind me right here. You saw the real thing. So this was a little video, and we were able to interpret what it meant. We could tell when there was a stream going, how old it was. So it provided lots of information about what Fremont looked like a million years ago. Okay, so just in case you never seen pictures of the second Fremont City Hall, I should have mentioned too that the first City Hall was where the community center is now, where the earthquake exhibit is. Well, they didn't learn their lesson on that one, so they built the second one um, right on that knoll. And this is the one that in 1989, when we had a large earthquake on the San Andreas Fault, cracked this and had to be demolished. And that's what the knoll kind of looks like today. Actually, it's really close to the pickleball area. Now, I want to take an understanding of how we got our hills. These hills here, as you can see in the left side, that cartoon, one is kind of going down. The Hayward Fault goes down within the lithosphere. And what it does is it pushes these up. So it's kind of going like this, but it's still pressure that pushes it up. So Mission Peak used to be underwater. We know that it's about 15 million years old. And if you ever go to Mission Peak, there's lots of shells. And what has happened in our area is that we've had a series of earthquakes that go up high, 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 high. And that's how Mission Peak got to where it is. But it's gone up so rapidly that our area is prone to gravity pulling this out because we call that the angle of repose is too great and the gravity pulls things down. So our area has lots and lots of landslides. Now, it wasn't until only about 10 years ago we realized that where the Hayward Fault started. It comes from the Calaveras Fault, which is south of San Jose. And that diagram on the right kind of explains that. There's a lot of information that will go. And let's just take a
We
real
were
quick
just
look.
looking at a relief map, how it shows over the plate
And how, if
movement
you
over
don't
millions of
trust
years
me
has
what to
created
doing, Debbie's going to
parallel
show
mountains and
you
valleys. A
how
simple
that works.
experiment, though, you can do at home. Simply use a piece of paper. Put your two hands down, and when you pull and push opposite directions, then you see how the paper starts to crinkle. Do you see those where you could be your mountaintops and what could be your valleys? You see you get parallel mountains and valleys. Now another thing other than just paper, you could try a piece of aluminum foil. Same thing, just flat out aluminum foil. I put my two hands, one's going to be the Pacific plate, one's the North American plate, and they're going to slip slide past each other. And as they slip slide, you'll see there, parallel mountains and valleys. So that's exactly how the mountains and valleys were formed in our area.
And how structural geologists actually do lots of studies on this. They call it rheology, where you're looking at how structures, materials actually react to stresses. And that gives us a clue of what's going on. So if you look at this area, see where San Francisco Bay is a valley, and you can almost see these lines. The San Andreas Fault is, hopefully you can see my cursor here, is in this area here in the north, and then coming to, this is San Andreas. So you have hills and valleys, and then this, and you have, excuse me, um, so you we have these hills and valleys that define our area. Now, just the last slide here. This is the evidence. When we plot all this down, we starting to understand more about plate tectonics and how it works. So where U.S. geological seismic stratigraphers and geophysicists, this is what they do to produce these maps. We don't know everything, but this gives us a clue of what is going on. So guys, I hope you learned anything. I think we have a few minutes for questions. Is that right? Let me escape.